Morning to all of you. Welcome to another session, and in this session we are going to discuss a very important topic from this thermodynamics. It is second law of thermodynamics. On the last lecture we completed first law of thermodynamics. In today's lecture we will complete second law of thermodynamics. So before I start, let me know if everything is all right so that we can quickly start the session. Is there any problem in the audio or video? Then let me know. Okay, so let's start. We are starting second law of thermodynamics. You see, why did you require second law of thermodynamics? We had the first law of thermodynamics, and what does it say? First law of thermodynamics gives you the law of energy conservation. Means energy can neither be created nor be destroyed. It can only transform from one form to other. But there were some limitations in the second law of thermodynamics. First law of thermodynamics. Like whether it will get transformed or not, whether any process will be possible or not, or what will be the direction of the heat transfer. These things were not mentioned. Like you have seen, if you have a hot body and cold body placed side by side, heat always flows from hot body to cold body. It does not flow in the reverse direction from cold to hot body. So this specification of direction was not given in the first law of thermodynamics. Okay. So it is impossible to transfer heat from a cold body to a hot body without applying any external agent. So these were the limitations of first law of thermodynamics. I have just summarized them for you. Why do we require second law of thermodynamics, or this is also the limitation of first law of thermodynamics? Okay. Good morning, Harry. Look at it. The first law of thermodynamics states that energy is conserved. This one is quite known fact and can be interconverted between heat and work. The heat and mechanical work, these two are equivalent thing, because first law of thermodynamics treat them on the same footing. So first limitation was it does not specify the conditions under which such conversions can occur. It does not determine the feasibility or direction of a thermodynamic process. Whether the heat will transform from hot to cold or cold to hot, it was not specified in first law of thermodynamics. So that was limitation, and that is why we require second law of thermodynamics. While it ensures energy conservation, it cannot tell us whether a process is possible or not. Second law of thermodynamics needed to address these gaps by defining the feasibility and direction of the process. Okay. This is why we need second law of thermodynamics. Is this understood? Any question from it? The limitation of first law of thermodynamics or the requirement of second law of thermodynamics. Now, if we talk about the second law of thermodynamics, it has various versions. Firstly, the mathematical version you can see. Second law of thermodynamics states that in any energy transfer or transformation, the total entropy of an isolated system always increases over time. The total entropy of an isolated system always increases over a time. For the timing, entropy will take a separate class on entropy. Actually, the next class will be on this topic, entropy and heat engines. So for the timing, you know, entropy is the measure of disorderedness in a system. So more disorderedness means more entropy. The total entropy of an isolated system always increases over time. Whatever physical processes happen around us, in each and every process, this entropy increases. Entropy decrease is not so feasible. ds is greater or equals to dq by t. It will not decrease actually. It may be 0. Minimum it may be 0. It will not be less than 0. So this is the mathematical form of second law of thermodynamics. ds greater than dq by t. Greater equal to sign is used for a reversible process when the process is infinitely slowly. So in that case you can treat ds is equals to dq by t. For other processes, irreversible processes, ds is greater than 0. So you will use ds greater than dq by t. Okay, this is the mathematical definition of the second law of thermodynamics. More popularly, these two statements are generally given for the second law of thermodynamics. One is Kelvin-Planck statement, another one is Clausius statement. Good morning, Ajay. What is Kelvin-Planck statement? It is impossible to convert all the heat extracted from a hot body into work. So as I mentioned here, it does not specify the conditions under which such conversions occur. So this one is given in the second law. It is impossible to convert all the heat extracted from a hot body into work. It means if you are transferring heat to some object, some heat is also wasted and goes to some other thing. Okay, it is not possible to convert 100% of the heat to work, let's say. Because if you consider a heat engine maybe, or the steam engine, you can say, in the old days, train was used to run by coals. So they used to burn coal and the train was used to, then the train was running. Okay. So if you burn some coal, in addition to running the engine, the some amount of heat is also wasted or goes to the environment. So you cannot get 100% of the extracted heat to convert 100% to work. So Clausius statement, it is impossible to transfer heat from a cold body to a hot body without expenditure of work by an external energy source. As I have told you, this process is spontaneously, it is impossible until unless you apply some external source in the form of maybe in the case of refrigerator or some you apply electricity to do this job. Without that it is not possible in normal scenario. So this is the main formula, ds is equals to dq by t. If you consider a reversible process, then ds is equals to dq by t. The theory part which we learn in thermodynamics generally deals with reversible process. So by default you will consider things to be reversible. Okay. So let's solve a problem. A sample of ideal gas with initial pressure P and volume V is taken through an isothermal expansion process during which process होगा क्या? During which the change in entropy is found to be delta. The universal gas constant is R, then the work done by the gas is. Can you do this? Hurry up, do it quickly. Are you able to do it? Look, you are given an ideal gas equation, ideal gas. So for an ideal gas, you know the universal equation. For an ideal gas, we know PV is equals to nRT. Okay, and it has been carried out by isothermal expansion process, and the change in entropy is found to be delta S. From the second law of thermodynamics, what we can write? Delta S is equals to delta Q by T. You can see ds equals to dq by T. So with greater than sign, we cannot do it. So let's say this is equation number 1, this is equation number 2. If you multiply both these equations, 1 into 2, if you do, what you get? P V delta S is equals to nRT times delta Q by T. This T getting cancelled. So from here you get the value of delta Q is equals to PV delta S by nR. What do you have to find out? Work done by the gas. So for isothermal expansion, what do you know? For isothermal expansion, isothermal means delta T is equals to 0. If there is no change in temperature, delta U, internal energy change, will also be 0. For an isothermal expansion process, delta U is equals to 0. Therefore, from the first law of thermodynamics, delta W is equals to, we know, delta Q minus delta U. So this is equals to P delta S by nR. Delta is 0. So option A is matching. Clear? Murali has not come. Joel, Anumita, these people has not come. Okay, let's talk about the combination of first law and second law of thermodynamics. So what does the first law says? First law of thermodynamics says delta Q is equals to delta U plus delta W. So P delta V, you can say, right? Delta W is P delta V. And second law of thermodynamics, what does it say? It says delta S is equals to delta Q on. Good morning, Murli. I thought you were absent. Delta Q is equals to T times delta S. Okay. So we can just combine this now. Combining first and second laws of thermodynamics. we get, let's put the value of delta Q into the first equation. So T delta S is equals to delta U plus P delta. So in terms of differential, we can write it as T ds is equals to du plus P. So this is the combined form of first and second laws of thermodynamics. Got it? Very simple. So this equation is very much useful. It will be used at different places. Let me give you one problem. The energy density and pressure of a photon gas are given by U is equals to A to the power 4. P is equals to U by 3, where T is the temperature, A is the radiation constant. Entropy per unit volume is given by alpha A T cube. What is the value of alpha? Entropy per unit volume. So what you have to find out? You have to find out del S by del V. If you keep the temperature constant, so it is actually asking you to find out del S del V at constant. Give it a try, Ajay, Murli, Harry. I think you can do it. U is what? Energy density. Energy is what? Energy is the internal energy. Energy density is energy per unit volume. So it will be U is the energy, internal energy divided by the volume V. So I have given you a lot of hints. Now I think you should be able to do it. Tell me the answer. A, B, C, D. So if you want to calculate del S by del V at constant T, we can use the combined form of first and second law of thermodynamics. TdS is equals to du plus PdV. If this is the case, if you want to calculate the entropy per unit volume, what thing we can do here? If I take derivative with respect to V, keeping T constant, what you can write? T times, you see S is no longer a single function, X is no longer a function of single variable. So as other variables are also involved, so we will write del. So del S by del V at constant T, treating T to be constant. This you can write del U by del V at constant. It is like dividing by del V plus P into dV by dV, that is 1. So, P into 1 is P. So, from here del S upon del V at constant T is equals to 1 upon P del U time by del V at constant T plus E upon T. Now, look at the question what is given to us. We are given U is equals to 80 to the power 4. So, let us say this is equation 1, equation 2. Now, what is given? Let us write that. Given U is equals to A e to the power 4. That means U is equals to energy per unit volume. This is equals to A t to the power 4. And hence U is equals to A e to the power 4 times this one. Option B is coming. Yes, very good. Very good, Ajay. Another thing is given P, pressure P is equals to U by 3. U is equals to capital U by V. So, U by 3V. Okay. So, U by 3V, U is equals to, we have got from here A e to the power 4 times V divided by 3V. A e to the power 4 by 3. Okay. Let us say it is equation number 3. This is equation number. So, we can write therefore del S upon del V at constant T is equals to 1 upon T del U by del V at constant T, del U by del V at constant T is 80 to the power 4 plus P by T. P is 80 to the power 4. So, 1 T is cancelled. So, 80 cube by 3. So, 80 cube plus 80 cube by 3, that is 1 plus 1 by 3, 80 cube. So, 4 by 3, 80 cube. 4 by 3 means 1.33 AT cube. And this is given to you alpha AT cube. So, obviously, the value of alpha is 1.33. Clear, Harry? Murli? Ajay have already done. Ajay has already done. Okay, let's move on if it is done. Try to solve this problem. The internal energy U of a system is given by U function of S and V. Lambda V to the power minus 2 by 3 S square, where lambda is a constant of appropriate dimensions. V and S denote volume and entropy respectively. None of the following gives the correct equation of state of the system. You do the problem. I'm doing my camera adjustment. Okay, let's try to do this problem. What is given to us? The internal energy is given to be a function of U, S and V. U is given to be a function of S and V, lambda V to the power minus 2/3 S square. So this is equation number 1. Now we can use the combined form of first law and second law of thermodynamics to find out this equation of state. So if you write the total differential of u, so du, if you write, you know the formula from mathematics, you can write it as del u by del s at constant v ds plus del u by del v at constant s dv. Let's say this is equation number 2. Now you require to calculate del u by del s and del u by del v. From the combined form of first and second law of thermodynamics, what do you get? dq is equals to Tds, this is equals to du plus Pdv. This one you know. We require del u by del s or something. So we need du. So what is du? Du is equals to Tds minus Pdv. To get du, let's say this is equation number 3. Now if you compare this equation 2 and 3, we get what it is. Are comparing equations 2 and 3, what you can write? Del u by del s at constant v is equals to t, and del u by del v at constant s is equals to minus t. Can I write it? Tell me. Just compare equation number 2 and 3. We can easily write it. We know u is equals to lambda v to the power minus 2 by 3 s square. So t is equals to del u by del s at constant v. So we have to take derivative with respect to s, keeping v constant. So lambda v to the power minus 2 by 3 derivative of s square is. So this is 2 lambda v to the power minus 2 by 3. Let's call it equation number. On the other hand, if you consider p is equals to minus del u by del v at constant s. Now you have to take derivative with respect to v with a minus sign, minus minus plus 2/3 lambda v minus 2/3 minus 1 minus 5/3 minus 5/3 h square is straight. Okay. Let's say this is equation number 5. Now, as you can see, we have s and s square. And in the options, you see there is no s. So we have to do something so that this s dependency goes away. Okay, because in the given question there is no sign of s. So if you want to remove this s, what you can do, we can take a square of this equation 4, then s square will come, and if you divide, then s square will get cancelled. What I mean, if you do like this, p, let's say p, it has s square divided by, if you do t square, the t square will give you s square. So this is 2/3 lambda v to the power minus 5/3 s square into, it is like 1 by t square, square of it. So 4 lambda square v to the power minus 4/3 s square. Then what will happen? This s square and s square will get cancelled, and you are left with this 2, this 2 will cancel, 1 lambda will cancel. So 1 upon 6 lambda, what will cancel more? Okay, v to the power minus 5/3 and minus 4/3, minus 4 by 3 plus 5 by 3, it is plus 1 by 3. 1 upon v to the power 1 by 3. And hence, we can write, if you have space, p v to the power 1 by 3 divided by t square is equals to how much? 1 upon 6 lambda. Lambda is a constant, so this is constant. And this gives you the equation of state. Pv to the power 1/3 divided by t square. So option A is matching, yes. So you can see how simple this question is. You just need the art of arranging things in a step-by-step way. So in addition to physics and mathematics, you need to have that art of arranging things in a proper manner. Then you will have less chance of making mistakes. If it is done, we can move forward to a new problem. Let me know if it is done quickly. Okay, try to do this problem then. The entropy of a gas containing n particles enclosed in a volume V is given by this, where E is the total energy, A is a constant, Kb is the Boltzmann constant. The chemical potential mu of the system at a temperature T is given by. This is really a short lecture, guys. This is the last problem we'll do today. In the next class, we will be starting heat engine. I should have made few more slides. Actually, these things are so easy. It is covered in less time. Look, actually, to solve this problem, you need to have little bit of idea of the formula which we already gave. So, look, dq is equals to TdS is equals to du. Here EU is represented by energy E. Instead of writing du, we are writing dE. Yeah, so first law, second law combined form plus PdV. Here another term is multiplied. If you talk about a chemical potential, it is minus mu T. Okay. So generally this mu dn is neglected. We go with this, but this term remains. You can use this formula to solve this. Look, if you want to calculate mu, what we have to do? You have to take derivative of s with respect to n, and this, if you want to make these two terms vanished, what you have to do to make du is equals to 0, we need to keep t constant and v constant here for to make dv equals to 0. Do it quickly, simple problem. After I have given you this formula, it should become very easy for you. Should be able to do it in 2 minutes, not more than that. This one we know. If you want to calculate, let's say mu, what it will be? Minus 1 is there, minus t is constant, del s by del n. Now what you have to keep constant to make d equals to 0? So you have to make t to be constant or e to be constant, and you have to make v to be constant. then we can write this formula, otherwise not. Now given S is equals to n kb ln ab e to the power 3 by 2 divided by e to the power n to the power 5 by 2. Now S is equals to n kb ln a v e to the power 3 by 2 divided by n to the power 5 by 2. Match it. A v to the power 3 by 2 divided by n to the power 5 by 2. Yes. Now we just need to take the derivative with respect to n. Mu is equals to, let's keep minus t outside, del s by del n. So what will you get? The problem is n is there inside the argument of the logarithm and n is also there here. Okay. So you can just write it as n kp ln a b e to the power 3 by 2 minus n kp ln n to the power 5 by 2 You can write it in this way. And what will give you, what will it give you? Option A is you are getting, yes, option A will come. So AB ln AB e to the power 3 by 2 minus 5 by 2 AB ln n minus 5 by 2 KB. Okay. KB is common in all the terms, so let's take KB outside. KBT ln, you see A V e to the power 3 by 2 and ln n, and we have no, so we should have not, okay, 5 by 2 will go up, so that will make n to the power 5 by 2 and this minus 5 by, it is the answer. Yes, option A is matching. Understood everyone? So this was a small lecture. I thought it would take time, but it gets completed very in less time. So in the next class, we'll be talking about Carnot's theorem, heat engine, and refrigerator and all. There is a slight chance that we'll take another session today in the evening. I will let you know. If I take, I will inform in the group. Okay, less likely, but I will definitely try to take it in the evening. Till then, bye bye. Take care. Have a great day, guys.